So Stuart Halloway is kind of exhausted from drinking from the fire hose of closure wisdom, or at least drinking, I'm not sure. So he called in a stunt Stuart to do the remainder of the introductions, and that's me. So our next speaker, Christophe Grand, is one of the authors of the upcoming book, Closure Programming, not to be confused with Programming Closure. And according to his blogger.com profile, his favorite movies are Blade Runner, Being John Malkovich, and The Nightmare Before Christmas. I think this has influenced his work on closure. So, Christophe Grand.
Thank you. Can you hear me? Okay. I'm here to document how I managed to turn a sequential computation into an incremental one. That is, how to transform one processing into differential processing, which will be able to compute, or rather to recompute the result of a function by only knowing the diff which is to be applied to its input at a fraction of the original cost. So in the beginning, there was a frustration. I always been frustrated when working on text editors by the fact that you can't reparse the whole input file at each keystroke. It's simply too much costly. And even minor things like changing the name of a symbol is going to cause the necessity to reparse the whole file to have a parse tree. And not having a canonical parse tree is a real problem, because in text editors, then you have to rely on Axe, on regex, on lexers, and they are all unsynchronized. And you rely on them for things like structure or syntax highlighting, for parents matching, and even for structural editing. And I had the intuition that there was certainly a way to take a standard parser and make it recompute the parse tree in sublinear time. In the best case, I thought that we should be able to recompute the parse tree in logarithmic time. Incremental is quite an overloaded keyword. In most of the time, you will be hearing about editors saying that they have an incremental processing. But in fact, what they have implemented is a restartable one. They checkpoint the computation along the input, and when you perform an edit on the input, you simply go back to the checkpoint just before the edit and replay the computation from there. Or there's a text editor named Y or Y, I don't know how it's pronounced, which is an Haskell editor, which is restartable, but which is lazy at the same time. So it doesn't have the pathological case of a restartable parser. Restartable parser have the pathological case that if you make the edit at the start of the file, you need to reparse everything. So E is better by being lazy, but if you do multiple edits, like in structural edit, where you decide to wrap everything in between parentheses, you have an edit at the start of the file, the other at the end of the file, and so even by being lazy, it won't be enough. You will have to reparse everything. So it wasn't enough. I really wanted to get the whole parse tree at only a fraction of the original cost. So from a very, very, very high-level point of view, a parser is simply something which consumes a stream of tokens, a stream of characters, which consumes a string. And it can be seen as a simple reduction. It's this expression, get tree, reduce per step init input. That's all. And many, if not all, computations can be reduced into something which resembles that expression. So the problem of turning parser into an incremental parser seems to be a general problem. So let's try to solve the generic case. And at LastConge, I promised to many people that parsley would be done before Christmas. But I never precised which Christmas. So by delivering it in June, I was way ahead of this Christmas. There were some details at the time that I had overlooked. So what I'm really interested into is on how to compute reduce per step init input prime when one knows the result of reduce per step init input and the difference between input and input prime. So there's a famous talk by Guy Steele about reduce being considered slightly harmful. The problem with reduce is that it doesn't put enough constraints on the functions. Your function can be nearly anything. And if you want to have parallelism, for example, you are going to want to have an associative function. And for incrementalism, it's the same thing, because incrementalism is parallelism with your former self. So associativity is pretty good. It allows you to turn a sequential processing like the slanted tree on the right, or on your left, into a balanced tree. And once you have the balanced tree, if each node is an item of the input collection, if you know that one item had changed, you only need to recompute all the parent chains, which is you only need to recompute a logarithmic number of nodes. But sadly, most functions are not associative. And a parser, by definition, has no chance of being associative because a parser takes a state and a token or a piece of characters and return another state. An associative function needs to have everything of the same type. But I stay determined to squeeze some associativity out of this radius. So we can picture a radius like this. There's the initial value, and at each stage there's f, which is combining the current state with one item. But if we break the collection to not see the collection anymore, each item is independent, and that we see each step like a pipeline, we can imagine that f and a are a partial function. So we can see a reduction like the application of several partial functions, here fa, fb, fc, fd. All these functions can be composed together to form a big composition. So here I have only 4 functions, but if I want to generalize to any size of input, I'm going to replace the call to comp by reduce comp over the collection of the 4 partial functions. And the collection of the 4 partial functions itself can be produced by a map over the original collection. I have the original collection. I map it to get a collection of partial function that I compose, and then I've got a big function that I can pass the initial state to, and I get the result value. And the good news are that comp is associative. So we are going to be able to organize the composition into a nice tree. So is this incremental yet? Indeed, it is. If I change C in C prime, I only need to recompute all the nodes which are in blue. So F, the first partial function and then the parent's composite function. But the problem is that it's only the composition which is incremental, not the computation itself. Indeed, if we picture the actual computation, the first time we go through the computation of the composite function. In this picture, each box is a function. The box with dashed borders are compositions. And the red arrow is the execution flow. So the first time we want to compute the function, we need to go through all functions. This is normal. And the second time, everything that is white is old function, old nodes of the tree. But still, we have to go through all of them. So it's quite ineffective. But in it, our input is constant. It's always the same state which is put as the initializer of the computation. And since I had the intuition of incrementalism, it means that most of the time things don't change that much. So let's try to memorize that. What I'm going to memorize, I'm going to memorize the results of map and comp. Really, the resulting functions are going to be memorized. This is not map and comp by themselves that I'm going to memorize. So if we memorize nodes, since the initial state is always the same, I can be sure that the second time I try to compute the composition of FA and FB, since the initial state is the same, I can skip the computation and go straight to the next. But then I stumble on FC prime, and FC prime is new. Since it's new, it's certainly going to return a new value. And FD, despite being memorized, won't be able to use the cached function, and so will have to be executed again. So it's better, but everything past the edit, everything past the item which has been modified need to be recomputed. So basically, if you have the composition tree and memorized function, you have the same behavior as for restartable parser, but a restartable parser is far simpler to implement. So it's still not enough. To go further, I needed to look into F. Right now, I have just talked about reducing a function over a collection without really talking about the properties of the function by itself. So now I have to look under the hood. And we have nice properties about parsers, and we certainly can use these properties to be able to build a better memorize. So what exactly our function is? A parser step function, that is the function which is executed for each token or each character of the input. And in the case of Parsley, I picked something very simple, good old allow. I just put something else which is the contextual tokenizer, but I put the contextual tokenizer for other purposes which are to make the parser total. A parser is going to return a parse-tree even if your input is completely broken. So LR, if you remember your compare lessons, it's a push-down automaton, and that is basically it's a one final state machine with two stacks, one stack for nodes and one stack for states. And at each step, the current state, that is the state of both stacks, is going to change. We are going to perform push, pick, pop on both stacks. But we never look at the entirety of the stack. We only look at the n top items of the stacks, and we never rely on the length of the stacks by themselves. So we ignore most of the data. So we really only depend on the top items of each stack. And by construction, since they are stacked, stuff accumulates during the computation on top of each other. So at the top of the stacks, you have items which have local meanings, and at the bottom you have items which have global or distant importance. So it means that we are able to predict what step is going to do only by judging the values at the top of the stack. So as long as those values don't change, we don't care about what's below in the stack. And this property holds true for composition of steps, which means that even if you are replaying 100 of steps, as long as the value you need at the top of the stack don't change, you don't care about what's below. So I'm able to perform stack transplantation. On the first call, if we have a stack of 6 items, and out of this 6-item stack, only the 3 first are looked at, and that the output stack is ZCDF, we can see that the modification on top of the stack, which is to pop A, B, and put Z instead, only rely on the fact that A, B, and C were there. So it means that when the next call arrives, if the new stack has changed but still have A, B, C at the top, I can take the bottom of the new stack and the top of the old result and graph them together. And this is what I call transplantation. But to do that, you need to have a kind of watermark during the first evaluation to know what is going to be useful. So it's kind of differential memoization. Usual memoization is going to only return a result if you pass in the exact same argument, while there I'm able to adapt past results to new inputs without recomputing the whole function. And so once again, if you do that for a big composition, you are going to save a lot of computation. Obviously, it still works like memoization. If the input is too different from what you already know, you simply call the actual function. So with transplantation, the execution looks like this. The first big white block is skipped like before because it's fully memorized. It's the same input, so we skip it. Then FC prime needs to be computed since it's new, but we are able to adapt the new output value of FC prime. And since we are able to adapt it, we can skip the actual computation of FD. So here we are really incremental since only the function which has changed has been recomputed. But in the worst case, if the differential memoization fail for FD, we'll have to recompute FD. So the worst case is going to be is going to have the same performance profile as researchable parsing, but it's not an all or nothing performance profile. There's a lot of things which can happen between recomputing only one node and recomputing everything past this point. I have witnessed some quite interesting pattern at some times where you have some nodes locally which are recomputed, then everything else past this point can be reused, and later on there's new nodes which have to be recomputed again because they are not corresponding to, for example, to a closing parenthesis which was modified by the first edit. So to perform transplantation, one needs two functions. The two functions which are needed are one which approximates dependencies between output and input. This is what I named the watermark, and it was figured by the dashed red line. And you also need a function to adapt a new input, a known output to a new input. But those functions are totally dependent on the algorithm. In fact, they are so dependent on the algorithm that I have only shown you the transplantation technique for the state stack. It's a completely different transplantation technique for the node stack. If I apply the same technique to the node stack, it would be too close, and the memoization will fail every time. To track dependencies, I must admit that I use side effects. I have collection, mutable collection, which are instrumented to tell me which items I have looked at, or which item I have pushed, and so on. But all this mutation is strictly scoped to the step function, so it won't leak out of the step function. And I have also changed the contract of the step function. Now the step function returns its result plus the watermark. So inside the step function, I have made many things mutable simply because at first I wrote everything in a purely functional manner. It was slow. I profiled it, and I see that I was churning too many objects inside the step function. So I made many things mutable, and it made the things easier because anyway I was already doing side effects to track the dependencies. And I also did another modification, which is that instead of looking at only one token, a parse step is going to work in a chunked manner so as to to reduce memory overhead of the composition tree, so as to not have one function per character, and also to reduce the context switches between being purely functional outside of the step function and being mutable inside. So the primary API is the buffer. This is what Parser exposes. There's the parser function, which returns the actual parser, and we simply take a grammar specification and some options. Then, with the parser, I create a buffer. It's really a buffer, like a text buffer. You can add characters and remove characters in the middle of the buffer. And you do that with the edit function. And once you have done all your edits, you call parse3 to perform the actual computation and get the parse3. One interesting property of having edit and parse3 is that you can work in a somewhat transactional manner. You can perform several edits which are not going to compute anything. Just change the composition of the function, and then parse3 is going to do the actual computation only once. So you don't have computed the intermediate parse3s. So I said that input is chunked. So if you remember, I have the input collection, so which is a collection of chunks. My chunks by default are lines, or several lines if the lines are too short. And I have simply one function to perform all the updates on the composition tree. Previously, all the composition tree I have shown were trees which were easily balanced because they had a power of 2 number of leaves. And to really implement the composition tree, which needs to grow and shrink as you add or remove characters out of it, I use a 2-3 tree where the leaves of this tree are the partial function we have seen before, the FA, FB, FC, FD, and so on. And the internal nodes are the composition. Plus, the nodes have to know their length. That is the length of the text which is behind the node, simply to be able to know where to perform the edit, which nodes to invalidate. Sorry. A finger tree may have fit, but it's easier to simply use a 2-3 tree, and I didn't need the privileged access that finger tree gave to both ends, because I'm only performing truly random edits in the middle of the tree. And another point was simply that I was a bit confused at some point between all the trees that were going around. There was the parse tree, the composition tree, and one or two others. So when we have seen how update is performed, it's pretty straightforward. If you perform an insert, it's going to grow the composition nodes below until it has enough children, and if the composition node has already enough children, the composition node will be split and the split will propagate towards the root. Delete is the other way around. If a composition node has only one child, it's merged with its siblings. So that's all. Now a little demo. it's a bit crowded. So let me first increment all the code, if only I can see. Oh, I can't see anything. Okay, so this is a simple parser for a simple S expression grammar, where I define here that an expression is either a list or a symbol, and the symbol itself is anything that matches this regex, and the list is the concatenation of an opening parenthesis, 0 or more expressions, and the closing parenthesis. Here are some options to specify that at the top level we can have any number of expressions we want. This one is just for the name of the synthetic root. And I also specify that between each token there can be spaces. So I evaluate this. Okay, it is evaluated. Tears and TP are only for pretty-printing. Here I'm going to create an empty buffer for the parser. That's done. And if I look at the parse tree of the empty buffer, I get this. But I pretty-print it, and it's simply root, an empty root. The pretty-printing is going to be vectors of first the name of the node and then the children. So we simply have an empty node named root. Here are some helper functions to generate some random input. Let's see. Okay, it looks correct. Here. So this is the random input I have generated. I'm going to try to pass this random input well, we don't see anything. So I added the empty buffer at offset 0 and for length 0, and I add the whole input into the buffer. And it takes some time, 15 milliseconds. And after that, I'm going to ask for the parse tree. So the 15 milliseconds were only for the composition of the function. So to really compute the parse tree, so to really perform the computation, it took nearly 200 milliseconds. Now I'm going to perform a little edit in the middle of the input. At offset 13, I'm going to change one character to S. Let's see where we are. Subs int. Okay, so I'm going to change one hello, certainly. So let's perform the edit. Okay, it took 1 millisecond to recompute the new composition, and now I'm going to reparse the whole thing, and keep in mind that I have performed an edit at the offset 13 in an input which is of nearly 5,000 characters long, So I'm quite at the start of the input, and parsing the whole thing took 200 milliseconds. Reparsing took this time takes only 6 milliseconds. And I have made the change at the start of the file. So really, I'm incremental. If I have been with a table, I would have recomputed everything in nearly 200 milliseconds. We can look at the resulting parse tree just to check that it is valid. So it's the pretty-printing, which takes some time. Or no, I didn't send the command maybe. It's coming. Yeah. So let's look at this. At the top, we should find an hello which has been changed to something else. No, I'm too high. Here we are. Okay, this was a minor edit inside the symbol. This doesn't change the whole structure of the file. We can try another kind of edit. We are going to add an open parenthesis at the start of the file and see how the parser performs. Okay, and now, so 1 millisecond again to compute the new composition and to compute the new parse tree 1/10 of the original time. And I have changed the whole structure of the parse tree. I have rebased it by adding a new node at the root. Pretty-printing again. Here we go. I'm trying to find the start. Wow. One window. I'm too high. Where's the I can't see anything. Here. This is what the new parse tree looks like. There are new unfinished nodes instead of where previously we had a root node and a list node. Because I have only inserted an open parenthesis without closing it, parse tree recognizes this and generates an unfinished node. But below that, past this point, it's the whole parse tree. Okay. That's all for the demo. And so what's next? I'd like to refine the way I compute dependencies, because the more fine-grained you are in computing dependencies between your input and your output, the more effective you are at reusing previous computations. And I'd like to to take some time to think hard on how to mechanize that. I think that it may be possible to automatically derive such functions from the original functions. What would be also interesting is to implement a more interesting, a more beefier parsing algorithm like GLR. And finally, this is some minor but practical feature I like to bridge with my regex DSL to make it easier for Laurent, for example, who is already using Parsley in counterclockwise to perform all the parsing, all the structural editing, but which has to maintain currently a grammar which is a bit ugly when it comes to token definitions. And I'd like also to make the parts which are imperative a bit nicer and to add better caching strategy. Right now, my memoization is just a one-shot memoization. I only compare to the previous result. And I'd like to use some pluggable caching strategy, but Michael Fergus has already done the library, so I only need to integrate it. Thanks.